Welcome to Ctrl+Talk. This is Anthony and Kate, and today we are diving headfirst into a story that has got the tech world buzzing.
Yeah.
Microsoft is saying they've cracked a major quantum computing puzzle with like a whole new chip design.
It's pretty exciting.
It is exciting, and it's not just the design itself. It's the scale of what they're proposing, a chip that could potentially handle millions of qubits.
Millions.
That's right, millions.
Yeah, that kind of processing power could change everything.
Okay, so for those just tuning into the world of quantum, let's do like a super fast breakdown.
Okay.
We all know bits, the ones and zeros that make our computers tick.
Right.
Qubits are like their weird quantum cousins. They could be a 0, a 1, or both at the same time.
Yeah, mind-bending.
It's mind-bending, right? And that's what gives quantum computers the potential to solve problems that would take our regular computers billions of years.
Exactly. And to grasp how big of a leap Microsoft is proposing, we have to look at where things stand now. Google's Willow chip has 105 qubits. IBM's Osprey boasts 433. These are impressive feats, but they're still baby steps in the grand scheme of quantum computing.
So this million qubit goal that Microsoft is kind of like dangling out there, that's not just an upgrade. That's like going from a bicycle to a spaceship. But
yeah.
Hold on a second. Wasn't NVIDIA's CEO Jensen Huang saying that practical quantum computing is still decades away?
He did, and that's why Microsoft's claims are met with both excitement and a healthy dose of skepticism. But here's where things get really intriguing.
Okay.
Microsoft's new chip, called the Majorana 1, is built on something called a topological core architecture. And it's this architecture that they claim holds the key to their ambitious scaling goals.
Topological core. Now that sounds like we're about to enter the realm of science shit.
And it does.
What's the deal with this architecture?
It's rooted in some seriously fascinating material science. Imagine a material that behaves like a semiconductor and a superconductor simultaneously.
Oh, wow.
That's what Microsoft says they've achieved with a topological superconductor. Or copaconductor for short. It's all thanks to this bizarre state of matter that's not solid, liquid, or gas, but something called a topological state.
Okay, now I'm really curious, what in the world is a topological state? And how does it connect to building a quantum computer?
Well, picture this. About a century ago, a brilliant mathematician named Ettore Majorana predicted the existence of this strange topological state of matter. And ever since, scientists have been on a quest to find the elusive Majorana particle, sometimes called a Majorana fermion. Microsoft claims they've not only observed this particle, but figured out how to control it.
Hold on, they're wrangling particles that have been theoretical for a century.
I know, it's pretty amazing.
That's some next-level science. So how does this particle taming translate into building a quantum computer?
It all comes down to the unique properties of the Majorana particle and how they interact within this topological state instead of relying on the traditional silicon. Microsoft is using a material called indium arsenide. Often found in infrared detectors at extremely low temperatures, this material becomes superconductive, which is crucial for maintaining the delicate quantum states needed for computation.
So walk me through this. They've got this special material. They've found this elusive particle.
Yeah.
And they're using them to build what exactly?
They're building qubits, but not just any qubits. These are what they call topological qubits. And they're theoretically much more stable and less prone to errors than other types of qubits. The stability is crucial because it means you need less error correction, which is a huge bottleneck in current quantum computing technology.
Less error correction? That means less hardware, less complexity? It sounds almost too good to be true.
It does, and that's why we need to approach this with cautious optimism. Right now, their Majorana 1 chip is only at 8 qubits.
Wow.
But they're saying the architecture has the potential to scale to millions. It's a bold claim, and the scientific community is definitely taking a close look.
8 qubits to millions? That's a gigantic leap. It's like saying you've built a model airplane and that it can be scaled up to a jumbo jet. What makes Microsoft think they can pull this off?
That's a great question, and it gets to the heart of why this announcement is generating so much buzz. It's not just the number of qubits, but how those qubits are created and controlled within this topological architecture. The stability of these topological qubits, in theory, allows them to be packed together more densely without causing interference, which is a major hurdle with current quantum computing designs.
So they're essentially claiming to have found a way to overcome a fundamental limitation of current quantum computers.
Yeah, that's a good way to put it.
But let's be real, even if they've cracked the code on stability scaling to 1 million qubits, still sounds like a Herculean task. What are some of the hurdles they'll need to overcome?
You're absolutely right. Even with this breakthrough, there are still monumental engineering challenges ahead. Building and controlling millions of qubits, maintaining those extremely low temperatures, integrating this technology with existing computing infrastructure, it's a massive undertaking.
Okay, so it's clear that we're still in the early stages here, but I'm dying to know, What are the real-world implications of this?
Yeah.
What could a million-qubit quantum computer actually do?
That's where things get really exciting. Imagine a world where we can design life-saving drugs with pinpoint accuracy, develop ultra-secure communications that are virtually unhackable, or create new materials with properties we can only dream of today. That's the promise of practical quantum computing.
Uh-huh.
And Microsoft believe they're on the path to making it a reality.
It sounds like we're talking about a world-changing technology here, but with all the excitement and buzz, it's important to remember that there's still a long way to go.
Absolutely. Microsoft's claims need to be rigorously tested and validated. We need to see independent verification of their results.
Right.
And the technology needs to mature before we can truly assess its potential. But if it delivers on even a fraction of its promise, the implications are staggering.
Well, it's definitely a story worth following closely, but before we get too carried away with the possibilities, I think it's important to dive deeper into the science behind this Majorana chip. How does this topological state of matter actually work?
Yeah.
What makes these topological qubits so special?
Those are great questions, and I think it's time we take a closer look at the mind-bending world of topological materials and the mysterious Majorana particle.
Let's do it.
Okay, all right, let's unpack this topological mystery.
Okay.
You mentioned the modded structure earlier.
Right.
It's a fantastic analogy because in a topological material, the way the electrons are arranged, they're very dense, dictates the material's properties. It's like a carefully choreographed ballet.
Uh-huh.
And that choreography makes the material robust against disturbances.
So even if things get a bit chaotic around them, the electrons in this material keep dancing their set routine.
Exactly, and that stability is what makes topological materials so exciting for quantum computing. Now enter the Majorana particle, our elusive guest star. It's not a fundamental particle like an electron, but rather a quasi-particle. Think of it like a collective behavior of many electrons, like that stadium wave we talked about earlier.
Right, the wave isn't one person, but the coordinated movement of many.
Yeah.
So this Majorana wave is made of many electrons behaving in a specific way.
Precisely. And what makes the Majorana particle so special is that it acts as its own antiparticle.
Okay, now that's just mind-blowing. It's like being its own mirror image.
In a way, yes. And this unique property is what makes them potentially ideal for building qubits. They're much less susceptible to noise and errors, those little disturbances that can throw off a quantum calculation.
So let me see if I'm getting this straight. Microsoft is saying they've created this exotic topological material, and within that material, they've managed to create and control these Majorana quasiparticles, which are then used to build their super stable topological qubits.
You got it. It's like they've created a fortress for their qubits,
Wow.
protecting them from the chaos of the quantum world, and that's why they believe they can scale up to millions of qubits, because each qubit is inherently more robust.
This is all starting to click into place, but I think it's worth pausing here for a moment to remind ourselves why this is such a big deal.
Yeah.
Earlier you mentioned life-saving drugs, unhackable communications, revolutionary materials. Can you paint a more vivid picture of what a million-qubit quantum computer could actually achieve?
Absolutely. Imagine a world where we can simulate complex molecules with absolute precision, allowing us to design drugs that target specific diseases with unprecedented accuracy. We could develop personalized medicine tailored to your unique genetic makeup.
That sounds incredible, but it's not just healthcare that could be transformed, right?
Not at all. Quantum computers could revolutionize cryptography, making it possible to create encryption methods that are virtually unbreakable, safeguarding our most sensitive data.
So no more worry about hackers stealing our credit card numbers or personal information.
Exactly. And in the realm of material science, we could design new materials with properties we haven't even dreamed of yet. Imagine superconductors that work at room temperature, ushering in an era of ultra-efficient energy transmission.
This all sounds like something straight out of a sci-fi movie, but it's potentially within our reach if Microsoft's claims hold true.
It's truly mind-boggling to think about the possibilities, but as we've discussed, we need to temper our excitement with a healthy dose of reality. There are still many challenges to overcome before we can truly harness the power of quantum computing.
Right, building a million-qubit quantum computer is one thing, but what about the software? Do we even have the tools and algorithms to program these machines?
That's another critical piece of the puzzle. We need to develop new programming languages and algorithms specifically designed to take advantage of the unique capabilities of quantum computers. It's like having a super-powered engine without a skilled driver.
And what about access? Will quantum computing be a technology that's only available to governments and large corporations?
That's an important question about accessibility. Microsoft's vision of integrating their quantum chip into Azure data centers suggests a future where quantum computing power could be more widely available, much like cloud computing is today.
That would be a game changer, making this transformative technology accessible to researchers, startups, and even individuals. But even with broader access, there are still ethical considerations to address, right?
Absolutely. As with any powerful technology, we need to consider the potential downsides and unintended consequences. We need to ensure that quantum computing is developed and used responsibly with a focus on benefiting humanity as a whole.
So it's clear that we're at the very beginning of a long and complex journey, but the potential rewards are so great that it's a journey worth taking. What do you think? What's the most important thing for our listeners to understand about this?
I think the key takeaway here is that we're potentially witnessing a paradigm shift in computing. Microsoft's claim, if it proves to be true, could be as significant as the invention of the transistor or the internet.
Wow.
It's that big of a deal.
It's like we're standing on the edge of a new frontier, and we have no idea what wonders or challenges await us on the other side. But isn't that what makes this so exciting?
Absolutely. It's the thrill of the unknown, the possibility of unlocking solutions to problems we haven't even imagined yet. But as we venture into this new territory, we need to do so responsibly and thoughtfully.
That's a crucial point. We can't just focus on the gee whiz factor of quantum computing.
Right.
We need to have serious conversations about the ethical implications, the potential impact on society, the workforce, even global power dynamics.
Precisely. Will this technology exacerbate existing inequalities, or can we harness its power to create a more equitable world? These are questions we need to start grappling with now, not after the fact.
It's like we're being handed a set of incredibly powerful tools, and it's up to us to decide how to use them for good or for ill. It's a huge responsibility.
It is, and that's why it's so important for everyone to be informed and engaged in this conversation. The future of quantum computing is not something that should be left solely to scientists and engineers. It's a future we all have a stake in shaping.
So for our listeners who are maybe feeling a bit overwhelmed by all of this, what's the one thing you want them to take away from today's deep dive?
Stay curious. Don't let the complexity of quantum computing intimidate you. Read articles, watch videos, ask questions. The more we understand about this transformative technology, the better equipped we'll be to navigate the exciting and potentially challenging future it holds.
Well said, and that's what we're all about here at Ctrl+Talk, making these complex topics accessible and engaging so you can be informed and empowered to participate in the conversations that will shape our future. Thanks for joining us on this incredible journey into the world of quantum computing and Microsoft's ambitious claims. Until next time, stay curious.